In the previous video, we've discussed about how a moving charge produces magnetic effects around it. Now in this video, we'll be talking about how does a current carrying wire produce magnetic effects around it. Here, you can see a wire where let's just assume there is a current flowing from this bottom end to the top end. Now, since this wire carries current, it's nothing but there are electrons flowing through this wire, and these electrons are charged particles. In the previous video, we have studied that any charged particle when moves, it produces magnetic effects. And so will this wire because it contains these charged particles. Consider a very small element in this wire, say of length dl, and the direction of this dl vector will be along the direction of the current flowing through this wire. Let's consider there's a point P over here in space at which we need to find out the magnetic field. The separation between point P and this element dl vector, let's say suppose is r. Here as you can see on your screens, r vector is the position vector of point P relative to the element dl. Now the angle between dl vector and r vector, as you can see, is theta here. In this particular case, the magnetic field produced at this point P will directly be proportional to the current flowing through the elemental wire. It will also be directly proportional to sine of theta, where theta is the angle between dl vector and r vector. And it will be inversely proportional to square of the separation between point P and the element dl vector. If we club all these proportionalities, we get magnetic field B is proportional to dl into I into sine theta divided by r square. Introducing a proportionality constant over here will give us the formula for magnetic field at point P, which is mu naught by 4 pi. So the formula of magnetic field produced at point P will be B is equals to mu naught by 4 pi times I dl sine theta by r square. The same formula can also be written in vector form. Now, as you can see in the previous formula, magnetic field B is proportional to dl sine theta. Here, dl sine theta can be written as dl vector multiplied by, or you can say dl vector cross r vector divided by r. So formula for magnetic field at point P in vector form can be given as B vector is equals to mu naught divided by 4 pi into I multiplied by dl vector cross r vector divided by r cube. Here you can clearly see that the direction of magnetic field is along the cross product of dl vector and r vector. So you can see here that dl vector is in this particular case pointing in this direction. Okay, r vector is along this direction. And now if we place our fingers along dl vector and curl them towards r vector, then you can see thumb is pointing in downward direction, which implies that the magnetic field at point P due to this current carrying wire is in downward direction, or you can say is into the plane. This law is called as Biot Savarts Law. With the help of Biot Savarts Law, we can find out the magnetic field produced by any wire in space. In the next section, we'll be talking about the magnetic field produced by different shapes of wires. Till then, stay tuned with Tutorac.